Hello, and in this presentation for computer organization, we'll be going over FP adders, control units, data modules, and the past related and truth tables related to them. So this assignment revolves around using AI resources to help us study this project and to help us with this presentation. The main resources we used were ChatGPT 5.0 and Gemini 3.0. Um, I found that the diagrams generated by Gemini were fairly resourceful and accurate, with some minor issues, but overall they were quite useful. So starting off with the FP adder hardware, this diagram is an official diagram for the hardware with all the steps. So it's not AI generated. Starting off with the sine, fraction, and exponent, these are broken up from the two numbers and evaluated. So we'll take the exponent from both numbers and it will go into the ALU, the small ALU, and this is used to find the bigger exponent between the two. The control unit receives exponent difference, and the mantissa of the smaller exponent must shift right, and the control unit will send a zero, send like a 0 1 to signify that. The big ALU afterwards is used to match the signs, and it will see if they are matching. Then it will do addition. If not, then it will be subtraction. Afterwards, we'll normalize the numbers by checking if there's an overflow by um, shifting right. If not, we'll shift left if it's an underflow. Furthermore, there'll be rounding hardware with the guard, round, and sticky bits to apply rounding, rounding it to the nearest even, and at the final part, we'll repack it all together to get the new number with the sign, exponent, and fraction, resulting in a 32-bit number. Um, for the for the format steps to turn a decimal number into this format with binary, first we'll look at depending on if the number is positive or negative. So we if we're converting it to binary, we'll have the leading digit be 0 or 1, depending on the if it's positive or negative, and then we'll normalize it by having it the lead number, the most significant bit, be one like 0 or 1. Even if the the actual value won't match because the exponent will make up for this. So the bias will get added to the exponent bits, and then the fractional bits will have the rest of the value, and then we'll drop the leading 1 or 0 0.1 in the fractional bits, and then at the end this will be all put together. And lastly, with our data path module, um, so the data path has a few components such as the operand decomposer. Um, this will help us with exponent compare and shift swapping, and then our alignment shift, significant add subtractor, and normalize and rounding at the very end.
So in this part, I'm going to explain the control unit. And this is the diagram that I designed. And this is the control hardware. It's basically in the floating point adder hardware, right? So in the floating point adder hardware, the control hardware unit basically controls hardware and decides how the data path should behave at every step. And it looks at exponent comparison and normalize mantissa bits. And based on that, it issues signals like big, small, shift, execute, and increment, decrement. I'm just gonna call increment, decrement, inc, dic for the sake of pronunciation. And these control signals tells the liner, the shifter, and the normalizer, and the rounding unit exactly when to act. So this table decides. So this part of the control hardware, and this is the truth table of that certain part. And this table decides which operand has the larger exponent. And if the MSB of the exponent difference is 0, that means operand A has the bigger exponent, so big becomes 1, and small becomes 0. And if the MSB is 1, operand B has a large exponent, and the big becomes 0 and small becomes 1. You just do the opposite. And in this part is the 0 detector plus execute control part. I just merged some parts into a single truth table in order to save space. So what this basically do is this block uses two zero detection signals, one looking at bits B31 through B24, and one looking at bit B23, right? And only one condition generates the clock pulses, when the upper block is non-zero and B23 is zero. So in that case, the round signal and the ink-tick signal and the execution signal all pulse at the same time. So basically it means they share one clock pulse, right? And this clock pulse triggers rounding or normalization when the mantissa is in a state that needs adjustments. So this table decides when the data path should perform an actual normalization shift. The shift and ink tick only activates in one case, which is when both the upper bits and B23 are detected as zeros. This means the mantissa is not normalized and needs correction. So in this case, the logic output shift 1 and ink tick equals 1. And in every other situations, both outputs remain 0, meaning the mantissa is already normalized. Okay, so this is the rounding hardware. We have to, in order to explain this, I explained the previous, what's it called? Yeah, control hardware unit. So the rounding unit basically decides whether the mantissa needs to be incremented after the addition and normalization state, which we just explained. And it does this based on 3 extra precision bits: the guard bit, the round bit, and the sticky bit. ChatGPT told me that. This bit tells us how far we are from the exact real result. Right? And then this truth table shows when the rounding hardware increments the mantissa. If all 3 bits, the G, R, and S, are 0, that means the result is already exactly representable. So increment is 0. If only the round bit is 1 but the guard bit is 0, we are still below the halfway point. So we also do not round up. If the guard bit is 1, if the guard bit, right, if that bit is 1 but the round and sticky, the S bits are 0, we are exactly at the halfway point. In this situation, just round up to nearest number, I guess. And finally, if all G, R, S are 1, that means we are more than halfway. In this case, we must round up, so increment becomes 1. So in one sentence summary, the rounding unit only increments when the result lies about the halfway point, or when the tie-breaking rule requests rounding to the nearest even value. Okay, so this is the 10.75 plus 0.125 operation process. And first, the decimal number 10.75 becomes, in binary, becomes that number, right? And then we just have to, when we normalize it, we just get, multiply by 2 to the power of 3. And for the next one, we just do the same thing. And basically, we're just gonna add this, and this is how it looks on the diagram. Thank you.